All right, guys and girls, so here's how this lesson works. As you're watching the video about relative dating and my lovely illustrations, you will be filling out your notes on your own document. At the end, you will have a problem right at the bottom for you to do on your own, and then you'll submit it into Google Classroom. Hi, boys and girls. Today I'm going to show you a little bit about how layers of sediment are laid down and how we can tell if layers are older than others. We're going to be looking a lot at the law of superposition. Okay, so to start off with, use my handy dandy markers here. The first thing we have to make sure that we all understand is that when sedimentary rocks are created, when layers are created, they're created from bits of sediment. So that means like different kinds of rocks, like tiny little bits or sand, dirt, other debris. They get laid, like they fall down like dust to the floor. So when that happens, we get a whole bunch of particles here. Over time, those particles go underneath a lot of heat and pressure, and then they solidify and form a layer of rock. There it is, our first layer of rock. Okay, so now let's say maybe this was a kind of a deserty environment, and so there was a specific kind of sediment, mostly sand, that formed this rock. It probably will turn into sandstone. And then let's say something happens with the climate and we start getting a lot more water in the area, and in fact the whole area gets covered by a sea. And so now we're going to get different kinds of sediment. We're going to get sediment form a lot from the shells of different creatures, from the a lot of calcium and pieces more, of course, more sand, but also now pieces of shell creatures. And over time, you're going to get more and more of these sediments laid down, and pretty soon we're going to have another layer of rock. There it is, our first layer of rock. Okay, so now let's say maybe this was a kind of a deserty environment, and so there was a specific kind of sediment, mostly sand, that formed this rock. It probably will turn into sandstone. And then let's say something happens with the climate and we start getting a lot more water in the area. And in fact, the whole area gets covered by a sea. And so now we're going to get different kinds of sediment. We're going to get sediment form a lot from the shells of different creatures, from the a lot of calcium and pieces more, of course, more sand, but also now pieces of shell creatures. And over time, you're going to get more and more of these sediments laid down, and pretty soon we're going to have another layer of rock. So there we have our second layer of rock. And you can see it's different from the first layer because of the stuff that makes it up. The other thing we should notice is that these layers are laid down horizontally. They call this the principle of horizontality. Basically, sedimentary rocks are always originally laid down or formed in a horizontal manner. Okay, sedimentary rocks do not form vertically, they form horizontally. Okay, so now over time, we're going to get different kinds of rock layers building up. Some will be thicker than others, some will be quite thin, but they're all going to be laid down horizontally. Okay, so now that we know what the principle of horizontality is, this is where you will be typing in your answers. Wherever there is the purple, that's where your answer goes. Okay, so at the end of this, all of these purple will be done. All right, so now some time has passed and we've gained two more rock layers. One layer that looks like maybe it was laid down when there was a big forest in the area, and another layer which is now the current layer that we're living on top of because it's closest to the surface. All right, so here's where the law of superposition comes in. We know that because sedimentary rocks are laid down horizontally and that they build on top of each other, that the oldest rocks are going to be at the bottom or further down, and the youngest rocks are going to be at the top. So when we're looking at relative age, we can say that the orange layer is younger than the blue layer. Or let's say through some sort of radiometric dating, we're able to figure out that this green layer is 30 million years old. Okay, and we're able to figure out that the brown layer is 100. If we're trying to figure out the relative age of the blue layer, we would be able to say that the blue layer is between 30 and 100 million years old. We might not know the exact age of it, but we can know the relative age of that rock. If you haven't already done so, please make sure you've typed in what the law of superposition is. So now we know the law of superposition, where the younger rocks are located closer to the surface, and as you dig down, the rocks get older and older and older. So if we know a certain rock layer, for example, this one right here, is 70 million years old, and this one way down here at the bottom is 100 million years old, what can we say about the age of this yellow layer? And then what scientific law did we use to answer that question? Here's another question. How old is this Sherman Shale relative to the Toroweap Formation? So here's what the actual landscape looks like. Here's with the layers showing what each rock layer is. Here's the Herman Shale. Here's the Toroweap Formation. So how old is this Herman Shale relative to the Toroweap Formation? Once you've typed your answer in here, make sure you write down how you knew that. Izzy, what do you think of all this so far? Do you like the layers of rocks? No? Okay. Well, anyways, this is where stuff gets really cool. Now once you know how rocks are laid down, this whole idea of the law of superposition, the next thing we can start looking at is stuff that happens to disrupt this neat, orderly line after line. Okay, one of the things that could happen is that magma from deep inside the earth, from the mantle, could start rising towards the surface. And when that happens, we get this like layer of igneous rock that could come in, okay? Usually it rises up and fills out like an area. We call this an intrusion. Intrusion. Now this intrusion, if we're now looking at it, we can see that the intrusion must have happened after all of these layers were laid down. So the orange layer is no longer the youngest here. It's this intrusion, this igneous intrusion. Okay, so if this igneous intrusion actually reached the surface and created, volcanoes above the surface, we could actually get a layer of igneous rock on top of this orange rock. That could happen. Okay. All right. now that we have all of these rocks layers, another thing that could happen is weathering. Now, if weathering happens, you're going to notice that some of this starts getting worn away. So here's an example of an illustration, a cross-section of an intrusion. So as you can see, without looking at layer D, we can see that E, C, B, and A have all been laid down horizontally. And then at some point, this intrusion came up from the mantle, this igneous intrusion, in through the layers. So we can see that it's cutting through E, it's cutting through C, and it's cutting through B. The first question here asks, how old is intrusion D relative to layer C? Well, in order for D to cut through C, it must have been newer or younger. So intrusion D is younger than layer C. How do we know? Because it cuts through it. All right, the next question is a little harder. How old is intrusion D relative to layer A? Okay, so what we can see here is that intrusion D goes up through B, but it doesn't really cut through A, which means at some point there must have been some erosion that took place, maybe, to get this all even, but then after that, layer A was placed down. So we can say that intrusion D is older than layer A because it doesn't cut through layer A. All right, the next thing that could happen is we could have some sort of an earthquake. Now, if an earthquake happens, the whole land is going to shift. So it could happen like this. Now, our layers are, you can see how they would still match up, but they're not laid down perfectly anymore. This is another thing that could happen to those horizontal layers. There could be forces, pressures that are pushing on it from both sides, and when that happens, the land kind of starts to buckle and we get these folds. Okay, so let's try and put all of this together. Here's a little more complicated picture. We can see we have some sort of layers. You can also see that folding that we talked about, as well as the evidence of some sort of an earthquake here with the line E. And our job is to label the relative age from 1 to the, which is the oldest, to 8, the youngest. Okay, so what I'm going to do first is I'm going to look at the layers. I can see that layer A is probably the oldest just because it's down the furthest, and so I'm going to put A right there. I'm then going to go with B for the next, then D, C, F, and then H. So what I've done so far is just gone straight from the bottom layer all the way up to the top. Okay, now we still have two things left. We have E, which is the earthquake, and we have G, which is the intrusion. So let's start with the intrusion. G is cutting through A, so it's got to be younger than that. It's cutting through B, so it's younger than that. It's cutting through D, C, F, and it even cuts into H. So it has to be younger than all of those. So I'm going to put G as the youngest. Now for the earthquake, E. So like the intrusion, we're looking at what layers are disturbed by this earthquake. I can see that A, B, D, and C have all been disturbed by the earthquake, so they must have been laid down before that earthquake happened. But you'll notice that layer F and layer H have not, so they must be younger, which means this earthquake E is going to go in there between F and C. Okay, so I'm going to have to adjust all these up. G, H now. This one is F, And then right in here is where my earthquake E is going to be. So there you have it. A picture that may look complicated at first actually isn't so bad if you start using what you know. Your task, now that we have gone through the different principles here of relative aging, is to take this cross section of Rockville, and there's the key, so it tells you what each of those colors are, and on your own you're going to figure out the relative age of all of these rocks. Okay, starting with 1, which is the oldest, and 8, which is the youngest. Now that we've gone through all the different properties of relative aging, your job is to take this cross-section of Rockville, with all the different colors of layers of rocks, and here's the key, the different types of rock, and to put them in order from the youngest to the oldest. So 1 here is the youngest. Oops, slight typo, I should say 12. 12, which is the oldest. As best you can. Once you are finished with this, go back and make sure that all of the purple areas on your document have been filled in, and then submit it into Google Drive.